Welcome to specific charge. Specific charge is the ratio of the charge to the mass of a particle. It's measured in the units coulombs per kilogram. For a proton, this value is 9.58 times 10 to the power of 7. A neutron, which hasn't got any charge, has a value of 0. And for an electron, this value has a magnitude of 1.76 times 10 to the power of 11, which is significantly larger than that for the proton. The calculation of this specific charge for an electron took lots of scientists many years to achieve. In the late 1880s and early 1890s, both Arthur Schuster, a British physicist, and Heinrich Hertz, a German physicist, were working on this problem, but they were using different techniques. Arthur Schuster was using the technique of a magnetic field. This technique over here. He understood that a charged particle would move in a circle if it was subjected to a magnetic field, and the force causing it to move in a circle was a centripetal force. So what he did is he understood that a centripetal force, which has this equation here, can be equated to the force of the magnetic field. And you can rewrite this equation for velocity. He also understood that the velocity of the electron that's fired into this magnetic field comes from it being accelerated by an electric field. Look back at the video about thermionic emission to see that the work done to accelerate an electron comes from this equation here. And what he did was he put this equation, that he substituted this velocity into here, and he was able to show the following. Which can be rearranged to give specific charge. The voltage that accelerated the electron into the magnetic field, the strength of the magnetic field, and the radius that the electron moves around are all known values, which means that he could calculate the specific charge. Now, at the time, he didn't realize that all of the work done to accelerate the electron went into its kinetic energy. So he thought that he was calculating a maximum possible value for the specific charge, when in actual fact, he was calculating the specific charge itself. And he came up with a value of approximately 10 to the 10 coulombs per kilogram, which is very similar to the value that we have today. It's a factor of 10 out, which has always remained a mystery, but it was the closest value that we had at the time. Unfortunately, because the number was so big, especially compared to something like the proton, this experiment and its results were largely disregarded at the time. Also, in the late 1880s and early 1890s, Heinrich Hertz was using an electric field technique to try to calculate specific charge. He was of the belief that these cathode rays were waves instead of particles, and some of his experiments were designed to show that the cathode rays behaved like waves instead of particles. One of the experiments that he had was firing cathode rays at a thin piece of metal foil. And he was expecting that if they were particles, then they would be blocked by the foil, but if they were rays, if they were waves, then they would pass through the foil. And that was the outcome of his experiment. But he didn't understand that electrons are so small that they were able to pass through the gaps between the atoms in the foil and make their way through. Heinrich Hertz's experiment was using an electric field to try to measure the deflection of these charged particles or waves as they went through this electric field. So this is the technique that he used. He had an electron gun generating these cathode rays. He passed it through an electric field, which was charged with a positive and negative plate, and he was expecting to measure the deflection from their initial path. Now, unfortunately for him, the way that he set up his equipment meant that he got a 0 result. He didn't actually achieve these results, but other people followed and were able to get the results that he should have got, including Jean Perrin, who is a French physicist, and J.J. Thomson, a British physicist. So let's have a look at that technique. So they had a positive and a negative plate, which created an electric field in this region. Something that's negatively charged will be attracted towards the positive plate, and anything that's positively charged will be attracted toward the negative plate. They fired negative electrons into this electric field and observed that their path moved toward the positive plate. They knew the initial velocity. They could measure the deflection of the cathode ray path, and they knew how wide the electric field was. So they could calculate, using some of this information, the time that it took the electrons to travel through that space. So here's the information they had in the x direction that allowed them to get that data. So we know s equals vt when there's no acceleration, and in the x direction there is 0 acceleration. The displacement in the x direction is w. We have the velocity and the time. They couldn't measure the time directly, so they could calculate it instead using these known values. In the y direction, so in this direction up and down here, they knew that the electrons were being accelerated towards the positive plate. So where you have acceleration, you have Newton's second law. And they knew that the force causing the acceleration was because there was an electric field. And the force of an electric field on a charged object is given by this equation. We can rearrange this for acceleration, which gives us but we don't know the value for acceleration, so we can't calculate the specific charge. The voltage and the distance between the plates, d, are both known. So we just need to calculate the acceleration, and that will give us the specific charge. And we do this by using SUVAT. Remember, we're in the y direction. So the displacement is known because that's y. The initial velocity is known, it's a value of 0. We don't know the final velocity in the y direction. We're trying to calculate the acceleration, and we do have access to the time that it was in the field because we have the information from the x direction. So this is w over v. This equation leads us to s equals ut plus half at squared. Ut, that term is 0 because u has a value of 0. So we end up with this equation here. And acceleration being equal to 2s over t squared. Remember that s is y and t is w over v. So this shows us that the acceleration is 2y over wv squared. Once we've calculated the acceleration, we can substitute that into this equation and calculate the specific charge of the electron. J.J. Thomson combined the two experiments to get a more accurate reading. What he did was he used the electric field which would accelerate an electron upwards, and he added in a magnetic field which would accelerate the electron downwards. And he balanced these effects so that the line of electrons was undeflected. So the path of the electrons was perfectly horizontal once he had tuned the electric field so that it was pulling up by the same amount that the magnetic field was pulling the electrons downwards. And when he had achieved this, he knew that the force exerted on the electrons by the electric field must be equal to the force exerted on the electrons by the magnetic field, which meant that he could write the equation and equate the two terms. The force exerted by the electric field is equal to the force exerted by the magnetic field. And if he rearranges this equation, he can get a term for the velocity of the electrons. The voltage divided by the strength of the magnetic field times by the distance between the plates. He then switched off the electric field. So the electric field, the force exerted by the electric field, was not there anymore. So his experiment now resembled this situation here, where there was just a magnetic force. And that meant that the electron was now moving in a circle, and he could measure the radius. Any object moving in a circle must be moving in a circle because it is subjected to a centripetal force, and that centripetal force was caused by the magnetic field. And the magnetic field was this. Rearranged for velocity, he can now equate these two equations because the velocity of the electrons as they enter the field hasn't changed. Notice that we have specific charge here, and we can rearrange and get an expression for specific charge. And there we have it. J.J. Thomson's value for specific charge of the electron was approximately 10 to the 11 coulombs per kilogram. He did further experiments to refine this, and we now have a modern understanding that the specific charge of an electron has a magnitude of 1.76 times 10 to the 11 coulombs per kilogram. So we now had values for the specific charge of an electron and the specific charge of a proton. And they are very, very different from each other. The specific charge for an electron is about 2,000 times bigger than that of the proton. And at the time, this was not understood. Now, when you have a ratio and you end up with a much larger number than you thought, it's either going to be because the charge is much larger than predicted, or the mass was much smaller than predicted. Now, because of Heinrich Hertz's experiments with the cathode rays penetrating the foil, it was thought that it must be the mass that was much, much smaller than originally predicted, causing this large specific charge. So just remember, when an experiment doesn't seem to go right, it's not always a complete loss. It might yield some other information that's useful further down the line.